I will talk a little bit about the technology, just so you're sort of aware of what the trade-offs are, more so than what the specific pieces of equipment are. Because again, any one of these could be completely obsoleted tomorrow by the latest invention that's out there. So, but we do have sort of have a suite of capabilities in our lab ranging from different material sources. So are you starting with a powder like that's going around in that canister? Is there a bed of powder, or are you actually feeding the powder in? Or do you have a wire, like in a welding system? Are you actually feeding a wire in and then melting that wire? And so the two different energy sources, laser or electron beam, you need a lot of energy to melt steel or titanium powder, right? So how are we going to be able to do that? And so we've got a nice suite of this. Gives us also a range, so not only are we looking at sort of different inputs, we also have quite a different range of size capabilities there. And so not to test you later on what the powers and radii and whatnot are, but just understand that some machines are really good at really small and very accurate, and some are very good at very big. Everybody sort of thinks, oh, all the machines are the same, but they're not. And some are really good for repair, some are very good for large scale, some are very good for small scale, and sort of, again, that's sort of a common misconception that, hey, they're all the same, I just got to buy one and pick it. They're all radically different in terms of what they can do. And the value proposition and the business case you need to make for each one of these types of technologies is very different as well. The Optimec, I think this is probably one of the most relevant sort of processes. This is called a directed energy system. And so what's going on here, unlike the laser and the powder bed, you're turning on the laser, creating a melt pool, and literally blowing powder into that and capturing it. And you move it back and forth and back and forth. Retract, laser goes up, repeat, repeat, repeat. And so again, you can build up a particular part. So now we're building this particular plate. One of the cool things about this is I can change the metal, the alloy, on the fly. So I actually have two different powder feeders. And so I can change the alloy as it's going. I can grade it from one material to the next. I can have a hard material here. I can have a soft material there. I can have a corrosion-resistant material there, whatever I'd like to do. So you now have that capability. And because it's a directed energy process, you have a lot more flexibility for repair and restoration. So the tool bit that I passed around there, repaired on this sort of machine. Put it in a chuck, spin it around at the right rate, deposit material. Rotocraft shaft, $6,000 part. Repair and refurbish for about $500, about 10 cents on the dollar. Get these back in operation. So I'll pass this around. This is probably the heaviest of them all, so be careful. But essentially, you're depositing material here and here. This is where the bearings are, and they grind that down, right? Well, let's just deposit material, and then machine it back down so it's in spec. I'm good to go. So again, $500, $600 on a $6,000 part.
Tim, what's the time to produce that?
To do the repair on that, maybe 3, 4, 5 hours. I mean, it's half a day probably. Probably the setup and everything is longer than it actually takes to deposit that. And that's, again, one of the advantages. This little nozzle with this particular system, you're trading off speed and accuracy. So this nozzle I can actually print in 20 minutes on that system. This in the powder bed, this would take probably 8 or 9 hours. So it's a little bit rougher, not as good tolerance. Again, these are the trade-offs. So all the systems that you're dealing with right now, speed versus accuracy, just like milling and the other processes. So fundamentally, the trade-offs are the same, but understanding, all right, well, it's the powder and the laser energy and those sort of things that all impact that. Okay? All righty, good. Sayaki then, last system. Actually, this is the big dog. This is welding on steroids, I call it. You can actually print let me show this. There's a picture of me inside of it, actually. 3 feet by 2 feet by 2 feet parts on this. And so it has an electron beam, huge electron gun that's coming down. Titanium wire is then being fed in here. Here is the rails where you insert the build plate, and then you actually build on top of that. And it's built in a vacuum chamber, and that's me standing inside the vacuum chamber. They literally had to take the walls off the building, the windows off the building to be able to get this in. I was hoping once it got in, they'd never be able to take it out, but somebody paid enough money, and they took it out last week. So the almighty dollar won on that one. But anyway, this sort of allows, Lockheed Martin, among others, looking at this technology. This is a picture from almost 20 years ago now when stereolithography first came out, the idea of let's just print a wing. With their big system up in Chicago, it's 20 feet by 8 feet by 8 feet. You can print a wing. Now, it's a lot of warping and you need some machining afterwards, but the technology is there now to be able to do that. And so they're actually producing components that are now flying, and being certified on the Joint Strike Fighter and other aircraft that using technology just like this.